square law demodulation. So for this square law, the input of a nonlinear device is going to be our S of t, and then the output is then going to be passed through a low pass filter, and then we get our message M of t. And as we are all aware, in the modulation technique for the square law method, the V2, which is the output of the nonlinear device, was given as A1 V1 of t plus A2 A1 square of t. Yet this is what was given as V2 equal to A1 V1 of t plus A2 V1 square of t, where A1 and A2 are all constants. So this is how we do it. This is the input. When you pass the input to the nonlinear device, this nonlinear device, since the square law, it will pass this input through this, and now we have our output as V2, which is equal to V out. And then from there, we pass the resulting V out through a low pass filter, and then get our message signal. Now let's look at the envelope detector, because at the end of this tutorial, we are going to take them one after the other. This envelope detector is more or less the same as the switching method, because we are going to use the same diode. So this detector is going to help us to detect higher level AM wave. Aside that, you have to note that the square law demodulator, it also helps us to demodulate a low level AM wave. So for higher level AM waves, we use the envelope detectors. So as I said, a high level AM wave demodulator, and then the other one is a low level AM wave demodulator. So let's look at how that one also works. For this one, instead of passing the M of t plus C of t as the input, we pass the same thing, S of t, as an input, which is our modulated signal. And here you can see that I was using the nonlinear device, but we don't use that. What we use is the diode. You make use of diode, and then from there, you pass the results through a low pass filter again, because it's the same concept and principle. And the final result is going to be our S of t, which is our demodulated signal. So this is the results after using the envelope detector. As you can see over here, it's more or less the same as, or it's making use of the same devices like the switching method during modulation. And therefore, sometimes I call it the switching demodulator, the switching method demodulator, instead of calling it an envelope detector. So the AM wave, which is the X of t, which is the input over here, is applied as an input to the diode, which is the detector, which is our demodulator. And at the end of the day, we are going to get an output. So sorry for writing this one here. It's not X of t. This is a modulated signal, M of t, because we are extracting the message signal. So it works in the same principle as we did for the modulation. In the positive half cycle, the diode will conduct. In the positive half cycle, the diode will conduct. So let's assume that this is our S of t, and this is our diode. So this is the input, which is V1, which is same as S of t. There's our output, V out, from here. We pass the resulting E out, V out to the low pass filter, and we are going to get our M of T to the load. And this will work in the sense that at the positive half cycle, this diode will act as a switch, and therefore it will conduct. The diode will be reverse biased at the negative half cycle. In that case, the diode will not conduct. So in doing demodulation here, we want to focus on the fact that when X of T is greater than 0, we are in the positive half cycle. We will see that our V1 equal to V out, which is equal to S of T. But remember that at S of T less than 0, our V1 is not equal to V0. We also agree that the V out for the switching characteristics of diode or the envelope detector, if you want to demodulate a signal, a modulated signal, as we did for modulation, we multiply the signal by a train of pulse, which is G of T. The train of pulse is like a duty cycle. We use it to control the switching of the diode, that is on or off, at a specified time or period that we want. And it's being represented by a square signal like this. Yes, this is someone we call a train of pulse. And we will use it, which has its Fourier transform to be 1/2 plus 2/pi cos omega ct, and we are going to use it in the near future. So now that we understand demodulation, why is it important? Because we have some various applications over here, and also without demodulation, as I said earlier, modulation is nothing. It's like putting your bag inside water. You want to cross river, and you have placed your bag inside the river. And because of that, you have been able to cross the river to the next end. If you have not been able to retrieve your bag back out of the river, it will seem like you have done constituency work. Therefore, it is possible for you to find a way to retrieve your bag out of the river, so that the mission of you being placed the bag into the river so that it can help you cross the river come and accomplish. So this is a little bit about demodulators, and therefore in my next video I'll be taking it one after the other, which is the square law demodulator and the envelope detector, and do mathematical analysis for them. So thank you for watching, and see you in my next video.